All right, team, this is lab 4, Monte Carlo simulations. Your lab document is here. That is an HTML file that will walk you through the Python lab, Jupyter notebooks. Here's this video, and then we've got some supplemental readings. This first reading is an excerpt from another textbook, Ong and Tong, and it gives you a couple of sections that are pertinent to this lab. So example 5.9 and 5.15 are here. It's a different kind of code that they give, but it gives you the same problems that we're doing here. These 3 other readings are background reading, and part of this lab is I ask you to read these and give a summary of some of the historical roots of Monte Carlo simulation, which came out of the Manhattan Project, developing nuclear warheads. All right, let's get into it. So here's our lab. Please read over the introduction. I'd like you all to provide an introductory paragraph and give 5 points for completeness of responses, narratives, making sure you all have good documentation of the steps that you're taking in markdown chunks as well as your code chunks. All right. I'll let you all kind of read over this. I give you a bunch of introductory material. Our first question here is related to those background readings. So take a look at that and give me a couple paragraphs on that. Now, the first few examples that I'll give you just run through how Monte Carlo simulation works. This code gives you estimates of pi we talked about in class based on the uniform distribution. So we take the uniform distribution to sample x values and y values between 0 and 1. And then we estimate pi using this equation right here that gives us essentially the ratio of points inside to outside of the circle. And this is going to be related to the area of a circle, which contains pi in it. Next, we look at how many samples it takes to get to an accurate representation of pi. Now, I could say, okay, what's the tolerance that we want to be under? And I could keep sampling until we get to that tolerance. But as you can see, we get out to 1 times 10 to the 8. So a really big number. This is a pretty crude way to estimate pi, but it's just kind of a dummy example to show you how random sampling can allow us to estimate things. The next example, and I should say that for your lab, I want you all to kind of copy and paste and make some comments along the way related to the examples that I give. So just kind of practicing that in Python. All right, so for this next example, we are exploring the wave height as a function of wind speed and lake depth and fetch distance. The same equation right here is what we used in lab 3, derived distributions. But now we're going to say, instead of just velocity having a distribution, the exponential distribution, we're going to say fetch and depth both have its distributions. And we would not be able to derive an analytical solution or an equation using the derived distribution formula. So now what we're going to do is, because we're saying all 3 of these variables have distributions, so fetch is normally distributed, depth is log normally distributed, velocity is exponentially distributed. We're going to take a sample from all of these and put those samples together to calculate a sample distribution for z. So we can't derive it analytically, so we're going to use Monte Carlo simulation to drive it directly. One thing to note is that the exponential function in SciPy stats is a little bit different than what we're used to seeing. We're used to seeing 1 over a times exp negative v, which would be our variable, divided by a. And so our rate parameter is lambda, or this value a. In this case, 1 over v naught for this particular equation. But the exponential distribution has a different form in Python. And so if we're going to say that lambda is 1 over 10, where 10 is our v naught value, our average value, In Python, we just give it the value directly, 10. So Python gives a little more simplistic form of that. So if we want to get a random sample from the exponential distribution, this is the function we'll use, expon.rvs, random variable sample. And then the parameter we'll give it is scale is equal to 10. So that's our v0 value. So just a little bit different, not a big deal. All right, so to do this, we're going to import norm, log norm, and exponential distributions from SciPy stats. And we're going to say our n is going to be 1 times 10 to the 4th as an integer. And I think I need to use a lowercase e there, but okay. We're going to give it the parameter values. So our average depth is 100 feet. Our standard deviation is 5. These are just, we're going to say these are the log normal parameters for depth. We'll calculate the log normal parameters based on those equations that we've used before. That's what we need to input into the function. Okay, so for normal distribution, we're saying that we have a mean of 1,000 and a standard deviation of 10 for our fetch. Our depth has a log normal distribution with sy and then mu y exponentiated. That's how Python needs it. And then for velocity, we're sticking with that exponential distribution and we're saying that scale is equal to 10. So that's our average v0 value. We're going to take a sample of n, which is 10,000 right here, samples. And then we're going to create essentially a sample of 10,000 z values. So we're just going to straight plug in the arrays of 10,000 values of f, 10,000 values of d, and 10,000 values of v. And so we'll plot that. And so now we get a histogram of that, those values of z. What I want you all to do is go back and find that continuous equation, that derived distribution for for z from the previous lab, and plot that as a smooth function over the histogram. So that's your next step. And then talk about why or why not it lines up or doesn't line up. And the hint there is that previously we only said v was a random variable. Now f and d are random variables as well with their own distributions. Okay, so the next example we'll look at is fairly similar, but we're going to do 2 steps here. We're going to first look at aleatory uncertainty, which is going to be uncertainty in the values of velocity here, and as well as the drag coefficients. So we're looking at an example, which is wind speed and the pressure that the wind puts on a building. And we're saying that the building will withstand pressures. It's going to impart those pressures on both the superstructure itself, so kind of like the shell or skeleton of the building, as well as the foundation. And both of these have some capacity beyond which they'll fail. So we're saying the superstructure can withstand 15 psi and the foundation 10 this is psf. The wind pressure can be calculated as this function. So we've got a drag coefficient c, some constant value, and then the v, the velocity squared of the wind, and that's in pounds per square foot. So we're saying that both the velocity and the drag coefficient are random variables. The velocity has this form, so exp 25. So 25 is our v0 value, and this is in the form that Python takes. And then we're saying the drag coefficient has a normal distribution with mean 1.8, standard deviation 0.5. So we're going to simulate using Monte Carlo the maximum wind pressure distribution using this relationship, this equation right here. And as before, we're just going to simulate values of velocity and drag coefficient, and then plug that in to get a distribution for wind pressure. So that's all I'm doing here. You can see I take my sample of V and my sample of C, and then I plug those in to get a distribution for the wind pressure here. That's what this green histogram is. And then I'm plotting the PDF as well as the CDF for the wind pressure. And I'm calculating that CDF by just doing the I'm sorting my pressure values right here from low to high. And then I'm calculating the empirical CDF by saying, okay, I'm going to plot the values of my sorted p-values and arrange them using this function here. So this is just the rank of each one plus 1 divided by the total number here. And so when I go to plot that, you can see that, where am I plotting it? My sorted p-values plotted against that cumulative probability distribution. And so it gives me a nice empirical CDF that goes to 1. All right, so I want you all with this, use the simulated data, the simulated p-values to calculate the probability that the foundation will fail in a given year. So that's just using the threshold for the foundation, which is right here, and just saying, okay, what percentage of observations fall above that value, and then use the risk equation to calculate that what's the probability that the foundation could fail. We'll just stick with the foundation here over the next 50 years. In this last example, we're going to look at incorporating epistemic uncertainty. So we'll use that aleatory framework where we're sampling both velocity and the drag coefficient. But then we're also going to create distributions of the parameters within those equations. So we're going to have a distribution for the mean drag coefficient, and we're going to have a distribution for lambda as well. And so there's going to be a distribution within a distribution. So here are the steps to do that, and make sure you read over this thoroughly so that you understand. So we're going to say, okay, as before, the drag coefficient has a normal distribution with a mean and standard deviation, 1.8, 0.5. Velocity is going to be an exponential distribution with lambda. Lambda is equal to 25. Now we're going to say that under epistemic uncertainty, mu c and lambda are uncertain themselves and will have their own distributions. So we're going to assign them coefficients of variation of 0.3 and 0.15. And then what we'll do is create a sample distribution for each of those parameters. And we're going to assume that they're normally distributed. So to get a sample for the mean and the lambda, the parameter distributions, we're going to use the normal distribution. And we're going to take 1,000 samples of each of those. So we're saying, okay, use the normal distribution, create a random sample. Here's the function for that. So give me 1,000 samples they're going to be centered on 1, and I'll tell you why in a sec. And then here's their standard deviation. So we're saying the standard deviation is in fact just the coefficient of variation. Later we'll multiply it by the means that will actually get the distributions of those. So I assign the standard deviation as the coefficients of variation of each, and then I get a sample of 1,000 for each mu, c, and lambda. So that's what I'm plotting here. Here's just this kind of normalized center on 1 distribution for the mean of the coefficient of drag and then lambda. Now we're going to plug those parameter distributions into the distribution for coefficient of drag and velocity. So that's this step. So we'll create an empty vector of 1,000, okay? And then we'll create an empty vector for this pressure, but we're going to call it P epi for the epistemic uncertainty. Now we'll go through, create another loop. We'll create a loop here. And for each value, so we're going to have 1,000 loops here, 1,000 runs. We're going to create 1,000 samples of coefficient of drag based on one of the samples of the mean of the coefficient of drag. So we're going to say drag has a normal distribution, and then the mean of it is going to be 1.8 times that centered on 1 sample. And so this is just one value. So each time this loop runs, it's going to give me 1,000, right? So size equals n, 1,000. 1,000 normally distributed values with a mean of 1.8 times whatever that kind of normalized mean of the drag coefficient is. And so same for velocity. I take my first lambda sample, I multiply it by 25, so that then kind of scales it, and then I get 1,000 samples of that. Then I plug those 1,000 samples of C and V in to create 1,000 samples of pressure. And then I concatenate, I basically add that to each run. So this starts at 0, it goes from 1, it goes all the way to n, and I'm going to get 1,000 plus 1,000 plus 1,000 all the way through estimates of the epistemic uncertainty. So at the end, I should have about 1 million samples of the wind pressure with this epistemic uncertainty. And now I'm going to run histograms of that and plot them over. And so the blue histogram is the epistemic. I made it on a log scale so you can see those tail values. It has a thicker tail, so kind of more uncertainty out in the tails. And then I plot the aleatory uncertainty from the previous example here as well. And so that's the P value that I'm plotting. And then I show you some box plots just to compare. I put it on a log scale just because there's a really big difference between them. And here's my aleatory, here's my epistemic box plots. You can see that the median values are pretty close, they're not too far off, but then the range or distribution of them are pretty far off. So for your questions, I want you to describe in your own words how we accounted for epistemic and aleatory uncertainty in this previous example. So what I just talked about, but I want you to make sure you understand it. So walk through the code to understand it. And then compare the distributions of these. And I'm going to change the text here a little bit just to say calculate the medians and give me the interquartile ranges and compare them using the summary statistics formula from before. All right, the last question is choose your own favorite equation. Whatever that equation is, it needs to have a couple or more random variables. Describe what it is, why is it your favorite equation? Pick at least 2 of these variables that you want to be random, and then perform an aleatory Monte Carlo simulation on this function, following the previous examples above, so example 2 and 3. So you're going to have to come up with distributions for the equations. What's the mean and standard deviation of your input variables, and then what's the mean and standard deviation of the outcome, the y value of the function of those random variables. So calculate a meaningful probability based on that sample, as we did previously, and interpret the results in terms of what your equation is and what your parameter values were. So this doesn't have to be super rigorous, just come up with an equation that has multiple parameters, come up with a distribution for that equation, and then parameter values for those distributions. All right. Good luck and have fun.